Welcome back to Integral Calculus. In this video, I'm going to look at the application of integration to the physics concept of work. If you have taken a physics course recently, you are probably very familiar with the idea of work from that course. It's one of the major pillars of the first course in the introductory physics sequence. If you have not taken a physics course recently or at all, don't worry too much. There's a lot of depth physically in what we can do with the concept of work, most of which I'm going to skirt over in this course. As I've mentioned in previous videos, this is a mathematics course, not a physics course. I'm going to show you some applications. I'm going to make you do a little bit of geometric reasoning in order to set up problems, but by and large, I'm going to give you directly in the statement of the problem the formulas you need to know in order to solve the problem. And the context is just giving you a little bit of why might something like this come up in the world. So, getting down into it, if you have taken a physics course recently, and I find that it is relatively rare that a student is taking second semester calculus and hasn't at least taken high school level physics to have been introduced to this concept. But you've probably seen a formula that looks something like work is force times distance times the cosine of the angle. And the physical idea here is if you apply a force to an object and you cause that object to move some distance, take the portion of the motion that happens to be in the direction the force is being applied and multiply those things together, and you get this concept of work, which really does relate to the colloquial idea of work, right? Doing manual labor. Grabbing a shovel and digging a ditch. You are applying a force to the dirt, causing it to move on the shovel and as you throw it, and that is physically what we mean by work. To make our lives easier, I'm going to just completely ignore that cosine theta term. I'm just going to assume that we're working with well-behaved systems where the force is pushing in the direction of motion and there's no motion discussed in the problem going in any other direction. That saves us a giant headache. The next thing I'm going to do from here is differentiate implicitly. On the left-hand side, the derivative of work I can write as the differential dw. On the right-hand side, we have a product, a force times a distance. Well, the force could be changing, so maybe we have dF times S, which we typically write in the other order, S times dF. Or we might have the force is constant and the distance is changing, so using the product rule. Why does that say control? I don't know what's going on right now. Sorry about that. Technology. Anyway, we're using the product rule here. We took the derivative of force multiplied by distance. We can then take force and multiply by the derivative of distance. For our purposes in this course, I'm generally going to assume that one, but probably not both of these, are constants. So either dF is 0 or ds is 0, which is going to make this problem simplify greatly and turn into something that we can solve. Not that you can't solve it otherwise, it just takes more effort than I want to put into things right now. All right, let me get my head out of the way and let's start digging in. There are two particular forces that I want to talk about in this video. The first is the spring force, the force felt by compressing or stretching a spring, which is defined using Hooke's law. And I want to go through this example because this is the most likely place that you've been introduced to working with a force that changes based on position. All right, so if I've got a fixed wall and a fixed floor, and I attach a spring to the fixed wall, and then attach the other side of that spring to a block which is allowed to slide about. Well, there's going to be some equilibrium point, some point where the spring is happy to sit there without trying to stretch or compress at all. But if you modify the spring by, say, pulling the block outward, then the spring is going to try to pull back in. And the force is going to be negative kx. We call k in this case the spring constant. It is a property of the particular spring that you are looking at in a particular scenario. There are situations where you might be asked to calculate that given an experiment, but for the most part, that's something that has to be given to you in the statement of the problem. I'm going to tell you we have a spring. I'm going to tell you we're dealing with a spring constant k equals some number. And I'm going to tell you that we're using Hooke's law, F equals negative kx. All of that information would be given to you in the statement of the problem. All right, I do want to quickly point out, remember x, as I've drawn it, is a positive value, and the force is pulling in the negative direction, which is why we have to put that negative in front. If we had compressed the spring instead so that x would be negative, then the force would be pushing in the positive direction, and a negative of a negative is still positive. All right, so the force is changing with respect to position. And with just that information, we can start setting this up. All right. So the work that is done by this spring is going to be the integral from the starting position 0 to the ending position s of our force multiplied by a differential, dx in this case. Right? That is what we have going on over here. We can, again, split things up. We can think about things. We can worry about things a little bit differently, but we're dealing with the small change in work at one particular point, negative kx. At this particular x value, you move a small bit of distance, dx, and then you go to the next x value and you do the same thing, and you do it over and over and over again. You add them all up, and you get this formula. Performing this integration, it's a little bit weird with that extra constant k there, but we're going to have negative 1/2 kx squared. We'll evaluate that at 0 and at s. Giving me that the work done by pushing this spring, or by pulling this spring by a distance of s, is negative 1/2 ks squared. The spring is doing negative work. The spring does not like doing work. In this case, the spring is fighting against the motion. Right? You are the one doing work by pulling on the block. Again, I'm not that worried about the physical meaning behind this. I'm worried about the application. But I did want to use this as an opportunity to go off to the side here and just point out that the energy stored in an object that has a conservative force, and the spring is a conservative force. Again, why and how, that's beyond the scope of this course. But we have a conservative force, so there is an energy being stored. The energy is the negative of the work done. In this case, that'll be positive 1/2 ks squared. And I like going through that little bit of it because this is probably an example that you learned about in that first physics class, and they said something to the effect of, and this step requires calculus and you haven't learned about the integral yet, so we can't do it. Well, now you've learned about the integral and now you see how it's done. It's not that difficult, but it's one of those places where physics classes and math classes tend to not be in lockstep with each other, so wherever we can pick up, we are happy to do so. All right, so there's one example. We have a force that is explicitly changing with respect to the position. The other example that I want to go through is a little bit more involved, okay, a lot more involved, but I think that's what makes it a lot more fun too. So, let's consider in this example a tank. I've got a cylindrical tank. Let's go ahead and set the height of the tank as 8. The units here are going to be in meters, but I'm not that worried about units. Again, this is math class, not physics class, and one of the reasons that I enjoy teaching a math class is that I can play fast and loose with the units and just say, okay, the units are 8, or the units are meters, the units are going to be kilograms, the units are going to be joules, newtons, all those units that you expect from a physics course. We're just going to trust that they all work out. I'm not doing anything that is going to make this a surprise in any way, shape, or form. All right, but the height of the tank is 8 units. The radius of the cylindrical tank is 5 units. And the tank is set up below the ground a distance of 6 units. Again, all my units are in meters, but that doesn't matter. We are going to fill this tank with a fluid whose density, rho, is 1,200. The units here would be kilograms per cubic meter, but again, I'm just trusting that all of the units are going to work out. We want to pump all of the fluid out of the tank. And with that goal in mind, the interesting question here, how much work must be done? And at first glance, you might not think this needs calculus, right? we're going to take all of this tank. We're going to grab the tank and we're going to lift it up above the ground. Well, that's weird. The cutoff of my camera is right at the ground level that I drew. Fun with green screens. Anyway, our goal here is to grab this tank and lift it up out. Well, not the tank itself, but all of the fluid in the tank. It seems pretty straightforward. But then if you think about it, well, the fluid here at the top of the tank has to be lifted a distance of 6 meters from the top of the tank up to the ground. And we're just pumping this into a trough that's at ground level, so we don't have to worry about things any further. But then as you go down through the tank, the fluid here has to be lifted quite a bit further in order to get to that ground level. So the distance that you are moving things is going to be changing in this problem. That's something we're going to have to pay attention to and be careful of, which is going to change our approach pretty dramatically. All right, let me get my head out of the way. In order to solve this problem, you need to know that the force that we're doing work against is the force of gravity. Force of gravity is the negative of the mass times the gravitational acceleration. And if you've taken a physics course recently, you were probably forced to memorize that the acceleration of gravity in the metric system is something like 9.8 or 9.82 meters per square second. But that rounds to 10. And if I round it to 10, that gives me some numbers that I can actually do stuff with without having to, bash my head against the wall or find a calculator, neither of which I want any part of. All right, so let's start thinking through all of this. I want to consider a small sliver of the fluid in this tank. Let's define that as position y, and we'll take y equals 0 to be the bottom of the tank. Well, this small sliver is infinitesimally thin. The height of the sliver is dy, but it is a cylinder and it has the same radius as the entire cylinder that we're dealing with. So the little bit of volume represented by that sliver would be pi times the radius 5 squared times the height, which is dy, or just 25 pi dy. Our fluid has a uniform density, 1,200 kilograms per cubic meter. If we multiply that by the volume, which would be in cubic meters here, then we can get that the little bit of mass of that little bit of volume is 1,200 times 25 pi dy. Right, 25 times 12 is 300, and then there's 2 extra zeros at the end. So that's going to come out at what seems to be a really large number, 30,000 pi. Right, but it's just a 3 followed by a bunch of zeros, which means it's still pretty easy to do math on. All right, so that's the mass of that little bit. The little bit of force acting on that little bit of mass is going to be the negative of gravity times that little bit of mass. Gravity is 10, so we're now at negative 300,000 pi dy. Yeah, that number looks scary, but it's just a bunch of zeros, and zeros are easy, so we can still do all this pencil and paper. We don't need to resort to a calculator. All right. And then the little bit of work that it's going to take to move that disk of fluid out of the tank is going to be the distance it has to go multiplied by that little bit of force acting on it. Well, the distance it needs to go, if I scroll back up and look at my tank, well, if the disk we care about is at the bottom of the tank, it has to go a distance of 8 and then a distance of 6. But it doesn't have to go the full distance because I've assumed it's already a distance y above the bottom. So it has to go a distance 8 and a distance 6, but we've already gone a distance y. So 8 plus 6 minus y, or 14 minus y. This is going to require a little bit of distributive property. 14 times 3 is 42. So 14 times 300,000 is 4,200,000. All right, we've got some ugly numbers going on here. I might factor 100,000 out. So we could write this as 100,000 pi times 42 plus 3y dy. And that looks a little bit cleaner, so we'll go ahead and do that. Now to figure out what W itself is, the total work. Add together the work done on every single one of these disks. There are infinitely many of them, so we'll integrate from the starting point. The bottom of the barrel is y equals 0, the top of the barrel is y equals 8, and we've got 100,000 pi times 42 plus 3y dy. Right? Antiderivative here. The 100,000 pi is just going to hang out in front. Antiderivative of 42 would be 42y. Antiderivative of 3y would be 3 halves y squared. Plug in y equals 8. All right, 42 times 8. Well, 4 times 8 is 32. 2 times 8 is 16. 320 plus 16 is 336. Eight squared is 64. 64 divided by 2. Wait a second. I knew something was going wrong here. I lost a negative sign. Sorry about that. I found my lost negative sign. All right, anyway, plugging in x equals 8 in the second term here. I'm sorry, y equals 8. 8 squared, 64. 64 over 2 is 32. 32 times 3 is 96. Plugging in y equals 0, we get 0. I love it when one of the limits of integration is 0. It makes life so much easier. And so we have 100,000 pi times negative 336 plus 96 is going to be negative 240. So all told, our answer is negative 24 million times pi. As is often the case in this course, that's an answer only a mathematician could love. That is in joules. Since pi is around 3, I could multiply that through. 24 times 3 is 72. So all told, gravity is spending 72 million joules of energy trying to hold that fluid in the tank, and you have to overcome it by inputting 72 million joules of work, which sounds like a lot until you start diving in, because this is a very large tank, right? A tank that is 8 meters tall and 5 meters in radius, that's 10 meters in diameter, is approximately the size of, I think that's a 2-story building. So this is a huge tank of fluid. There's a lot of fluid being pushed around here. If you just calculated the total mass of the fluid and multiplied by the total distance the tank has to go, you'd find that moving the entire tank is quite a bit more energy than that still. But, yeah. I wanted to go through this one specifically because it is complicated. It requires a lot of thought and a lot of reasoning things through as you work through it. I will end, as I so often do, with one for you to try on your own, which is definitely going to be easier than that last one. So let's consider a coil of rope with linear mass density rho equals 3, and I've even given you the units here, it's kilograms per meter. I want you to calculate the work needed to lift one end of the rope 5 meters into the air. And we'll assume that there's enough rope that most is still on the ground. All right, so the idea here is I've got some sort of a crane or a hoist or something that has grabbed one end of a coil. And that one end of the coil is now at a distance of 5 meters above the ground. Most of the coil is still sitting on the ground. Before you get started on this, I do want to give you one hint. Because you are lifting from one end instead of lifting up the entire thing, the amount of mass that you're actually pulling is going to change as you go up, which is going to change the amount of force acting on this thing. So think about it from that perspective. Think about how much force is there at one instant along the rise, and then integrate over the entire raising of that rope. With that idea in mind, the formula for gravity we just looked at in that previous problem. See what you can do with that one, and I'll see you in the next video.